Can we do linear algebra?
Can we do linear algebra?
Please.
No. We did one sentence of linear, like last class we did what, 15 minutes?
Yeah.
10 minutes? The last review. All right, on to chapter 4. So we've been doing maths. I hope I wasn't too offensive. That's actually been surprising. It's like, anyways, how about that? We've been doing maths and that whole idea of toys and rules. We started off our class with logic. And what were the toys? Starts with a P. Propositions, things that we declare to be true or not, right? These sentences. What were these rules? We had things like and or, and then, etc. We talked about logical equivalencies and arguments, which are always fun. People have a throwdown. And then proofs. Right? All these sorts of things that, and applications of it. And so we had all these rules. We had an entire, just here's your stuff, put it together, immediately have an exam, then we rebooted, and we had sets. Okay, and the toys were sets. It's always fun. We have set theory. What's our toy? Sets. So we had intersection and union and cardinality of a set, and a set cross a set. All these other sorts of things. We asked for equality of sets, applications of sets, were things like functions and cardinality. Cardinality is kind of a fun one on that one, where we have the idea of, we did sets, and at the end of it, we, with the idea of functions, which are just a part of sets of ordered pairs, the rules that generate those such things. Cardinalities, again, it's kind of interesting that we talked about naive set theory. And from naive set theory, stronger definition was axiomatic set theory, was cardinality. This question of, we now know, at the very end of this section was the cardinality of the reals, if you would have read that section, are equal to the cardinality of the power set of the integers. And one of the things that's kind of an open question is what's called the Continuum Hypothesis. And the power set of here is 2 to, what's the cardinality of a power set? It's 2 to the cardinality of the set, which would be 2 to the Aleph null. And you sit there and say, that's a big type infinity. What is this? What's Aleph null? It's a measure of a non-finite, right? The same thing as these sets. The Continuum Hypothesis gets to this question of, do all of the infinities order nicely? Where we, whoops, that's supposed to be a 2. We go up, and like this would be things like, okay, that would be 2 to the Aleph null, because we'd be talking about power sets. Everybody over here is the whole idea of the countables, right? And these would be 2 to the z's, which cardinality-wise is the same thing as the reals. And so we can act like, well, this next size of infinity is the reals. And then the next size of infinity is the power sets of the reals, which would make some really big, complicated-looking sets. Because what are the infinite ways to take any combination of real numbers as a subset of the reals? So you can imagine this thing is 2 to the power of Aleph 1. The continuum hypothesis is those infinities are discrete. They're either countable, or they're like the reals, or they're like the power set of the reals, or they're like the power set of the power set of the reals, and there's nobody in between. They're just a nice, countable group of countables to uncountables to, I don't even know what we'd go up, what we would even call those new names, but this is an open question. It's a hypothesis. What they have proved, though, is that we can't show it's either right or not. I can't disprove it, and I can't prove it with our current understanding of sets. If we would write sets, go past naive set theory into a well-defined idea of sets, axiomatic set theory, they've gotten to at least this point. I can't prove it or disprove it. Right? We're stuck. We don't understand sets enough. It's kind of an interesting barrier to simply say that unordered collections of stuff, we don't understand that well enough to get to this idea of sizes of the non-finite. We don't have enough math yet. We don't have anybody that's approached it and tried a different way. So it's kind of this nice little barrier that's like kind of just sitting there, just saying it's like you would assume that unordered collections of stuff would be, well, doesn't that get it? And here's like this problem that sits there and says, nope, that's not good enough. So you can't either prove or disprove this with what we understand. So either we change what we understand, like what does it mean to be a set, or maybe it's one of those classic boundaries that'll be we accept it. I don't know. All right, as we go through it. So it's kind of interesting as you get through maths themselves, all these things of all these different toys and rules. It has very interesting open problems. The next thing that we're going to do now for chapter 4 is what I'm going to call baby number theory. The book calls it number theory. If you want to take number theory, I think that's a 600 level class here. I'll call this baby number theory because it's like, unless I'm not interested in linear algebra, we had one section to say, can you add, multiply, join, meet, or Boolean product these matrices? It's like, we weren't really interested in the deeper issues of it. We'll do some number theory. Along with this, we're going to cover one particular application, which is going to be cryptography, which should obviously be very, very important to all of us because, well, with the advent of the internet, cryptography is rather important. Right? Who was it? Who did T-Mobile use for like securing their data and stuff like that? And they got hacked and so all the people's stuff. But they were like, well, yeah, they got everything, but everything was encoded with a 2048-bit level encryption, so they just got the encrypted data. And it's like, okay, I wonder what that means. Do you trust that? What does it mean? Is it there's 128, there's 256, there's 512, there's 1024-bit, there's 2048-bit? What are we talking about? And we're actually going to do that cryptography, not that level of cryptography, but we're going to get to the point of what crypto is. Crypto is, honestly, number theory plus an understanding of functions. Because cryptography, the simplest cryptography I can think of is speaking in another language. Right? What's red in Spanish?
Rojo.
All right, somebody comes and says Rojo, and I'm like, I have no idea what you just said. Right? They've encoded it to me. And it's like, well, now I got to go back to red. They say, and so somebody that knows Spanish can, all right, what's encryption and decryption? It's an invertible function. We either take a symbol into another symbol set according to a function. Let's say I know English and Spanish, and then we decode it from Spanish back to English. Okay? And you can do symbols or ideas. And like real old ones, like we talk about the Romans, they would shave the head of a slave and tattoo the back of it and let the hair grow out and then go. And that's their cryptography method. It's like, just don't tell anybody there's something on the back of your head, right? And so it's like, that's my secret. And so, but on the other hand, what's the encryption method? I let his hair grow back. What's decryption? I shave it, right? It's an invertible function, except we're going to do it under the ideas of numbers. So we'll have one number set. Every number represents something. Like the number 1 could represent red. The number 2 could represent blue. We could encode ideas, or you could encode letters, A, B, C, and we'll just move them from one set to the other. All right. But to do that, this is kind of where a big part of discreteness comes from. The toys here are going to be the integers. Classically, we're not the integers, we're talking about the positive integers. Because classic, they didn't have 0 or negatives, right? If you did number theory in the times of the Greeks, it would be 1, 2, 3, 4. And these had deep meaning, right? And you would go through it, and everything was integer-based. Obviously, we can get around things, like if I said, okay, well, what if I had, say, 6 11ths, right? Well, 6 11ths doesn't exist as it is. Doesn't exist in number theory. It makes no sense. And he would say, well, why not? Well, on the other hand, I could always deal with it in number theory, right? If I wanted to deal with it in number theory, what is it really? As a number theory, what this would represent is 1 in 11 parts, and then you would need 6. You take unity. You would break unity into 11 components, and you need 6. That's your new unit. Right? Each of those smaller pieces is now unity, and I now need 6 of those. And that's what 6 11s mean. So in the end, integers are good enough, right? I can represent these things however I want. Thinking about it like that, square root of 2 being irrational becomes very interesting. Because what does it mean to be rational? What it means to be rational is that you should be able to take a unit, break it up into so many pieces, tell them how many pieces those needs, and that will be exactly that length, or exactly that amount. Square root of 2 says that cannot be done. It's like, well, what if I use really, really tiny things? It cannot be done. The Greeks had fun things with the ints. You had male numbers, female numbers, effeminate numbers. Right? You had all these sorts like this is unity, and then all these other really to kind of go through there. It was numerology as much as number theory. Like they had deeper meanings behind stuff. But for us, it actually introduces kind of an interesting feature. We have a problem in that you are modern Americans, and because you are modern, well, people in America, it depends on what you want to declare yourself, right? So we're all here. And so we have a big problem, which is division versus number theory. A big part of this, number theory has no division operator. Okay? All right, what am I talking about? All right, 2 over 7 versus 2 divided by 7 versus 2 divided by 7. All those are the same thing, right? All of these as the idea of division. Division is an op that where what happens? 2 reals go in and 1 real comes out. That's what division is. We write 2 sevens and you get a decimal, right? Write a decimal, you do your long division. All right. This is another reason why number theory is lacking within modern thought. How many? Well, modern usually within the last 2 generations. We don't do enough with numbers. We don't do enough with ints. Right? We don't. How many of you guys actually do your math, your arithmetic, for your daily life? Do you know how much you're going to spend at the gas pump before you pump it? Do you know how much you spend? You're coming up with your shopping cart. Do you know within, say, $1 or $5 what is in your cart before they ring it up? Or do you just simply say, boy, I hope I have enough?
Yeah.
Right? That really gets to the point where we don't deal enough with numbers. Well, guess what number theory is? Think about numbers, think about numbers, think about numbers, and they're only ints. And you think about them, think about them, think about them. Well, this obviously does not exist within number theory because these are not integers. Right? This is not an integer. This is not an integer process. And because this is not an integer process and number theory is integers, this makes no sense for us. So there is no such thing as a division operation. But number theory does have, and this is where we get the struggle. So are you okay with when I say the word division and I mean division operation, I mean 2 reals come in, 1 real comes out. When I say 2 sevens, you think of a decimal that spits out the other side. You plug it into a calculator, you do it by hand, right? 2.000, right? How many times does 7 go into 2? None. How many times does it go into 20? Twice. 14, 6, 0. How many times does it go into 6? Well, none. How many times? Bring it on to 0. How many times does it go into 60? Down, 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 down. Is everybody okay with that? We would just simply do this process. 2 reals went in, a real comes out. That makes no sense for number theory. Number theory has at its heart the first, in terms of number theory operation, okay, our toys are obviously just simply the ints. Our rules, or my ops, plus times. Minus is plus, right? 5 take away 3 is really 5 plus a negative 3. So I can actually just simply define it as plus. Times. What's times? Times is definitely what the word means. 3 times 5 is 3 plus 3 plus 3 plus 3 plus 3. Multiplication is literally multiple additions. That's why the word is what it is. And that's why we learn it. We just simply memorize that 5 times 3 is 15, but how did you first memorize it? By doing the addition. And so in the end, we really have just addition, because multiplication is just a shorthand of addition, of many additions. But we have a new one here, which is going to be a bar symbol, A bar B, and this is new to us, and this reads A divides B. This, in particular, is not an operation in terms of numbers come in and numbers come out. This is a propositional function, right? This is a propositional function. What are propositional functions? Stuff comes in, but what comes out? True, false, which is really, I could say, yes, no. And so the idea here is A, B go in, and out is true or false. Right? The idea behind this is sharing. Mathematics has a purpose, right? We are modeling things. We are not just simply creating it just to simply goof around, right? It's about, I'm going to model this, and this is a purpose. Go back several thousand years. All right, let's go back to the age of pirates and treasure, right? And you have this idea of, all right, they have the treasure's all sitting here, and all the pirates come around, and they're going to share the treasure. All right, so we have young children that are playing pirates and treasure, and I'll have a pile of candy, and there's 6 kids around, and like, what do? They share. One for you, one for you, one for you. When I say share, I'm talking about what? Sharing fairly, sharing evenly. Everybody gets the same amount. And the answer is either I can do it or I can't. Like if you have leftovers that you can no longer share, you would look at that and say, oh, well, I can't share that amount. Well, if it's pirates and treasure, we'd now have stabby stabby, fewer pirates, and then more treasure for each of us, right? As we go through it. But it's about a question of sharing. And so the idea is really this. Can A people fairly share B items? Yes, no. That's divides. Now, if you would look at this, does divides, is it naturally commutative? Well, that commutativity makes absolutely no sense, because the people on the left are people, the things on the right are stuff, right, that you're taking. Now, I could write a number on the left and a number on the right, but they're different meanings, right? They have different purposes. So if we would go through this, in the end, it's just simply a yes or no. And so we have examples. Could 3 people divide 12 things? Yes, right? How did you know? Because each of the 3 would get 4. In your head, you turned it into a multiplication, right? You would say yes. And what you did, it was because 3 people get 4 things, which is the 12, right? Everyone gets 4. And so you would say yes. And so 3 does divide 12. On the other hand, does 3 divide 13? Why did you say no? If I tried to do it, there is no integer. Well, we could just simply do this. Because 3 times 4 is 12, and what's the next int? Right? I can't share the stuff in the middle. Right? One way of looking at that, it's like, oh, look. So 3 times an int equals 13? Never. So that's why I said no. On the other hand, if 3 does not divide 13, we would usually write this as 3 does not divide 13 is true, right? It is not the case that 3 divides 13. And so that would evaluate to true because I'm just simply negating the no, and it becomes a yes. This is what we do when we say divides. And we also have, you look through different numbers over history, and you have things like, okay, why is it, we were talking about sharing, why in English do we have a unique word for everything up to 12? And then everything after that is a combo. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are all unique words. 13 is 310, right? It's addition now. 14, 15, 16, 17. Teens meaning the 10, right? 20, 20, 10. 21 is 20, 10, and a 1. We're just using addition now. My words mean literally what you're doing under addition and multiplication. All right, why is it we have unique words for 12? Well, why would 12 be important? Well, when we look at this, does 1 divide 12? Yeah, if one person comes up, can they have everything? Of course. Does 2 divide 12? Sure. Does 3 divide 12? Yep. Does 4 divide 12? 1, 2, 3, and 4 all work. What's the next one? Does 5? No. But does 6? Yeah. Does 7? No. 8? No. 9? No. 10? No. 11? No. 12? Now, here's a kind of a little note. For all numbers, at least the front and the end work, right? One person can have everything. If you're the pirate, kill everybody else. The treasure is yours. The other way is to have as many pirates as treasure, and then we all get one, and we're all happy. No. And then we have the middles. What's neat about 12? 1, 2, 3, and 4 work. So think about all the ways those work as combinations. If you have 12 people, could you break them up into one group, two groups, right? 2 groups of 6, 3 groups of 4, 4 groups of 3, 6 groups of 12, or just, one group of 12. So you have all those ways of working it out. That's one of the reasons why we have unique words up to 12 with the many cultures. All right. Obviously, me saying words like, can A people fairly share B items? Yes, no, is a pretty bad mathematical definition. So let's use lots of symbols and math words. All right. A divides B, for A and B are integers. A cannot be 0. Why is that? Why do you think that's true? If nobody shows up to share, does that make any sense? How much does nobody get? What do you mean nobody came? Nobody came. Well, what are you talking about sharing then? Share. Well, but there's nobody here. Well, that doesn't make sense. So we just skip it, right? If nobody shows up, sharing doesn't work. All right, so we leave that out. And this is a logical function. And I say this is true if and only if there exists some c that is an integer such that a times c is equal to b. On the other hand, in other words, what did I do? See that? That 3 and 4? 3 divides 12. Why? Because 3 times 4 is 12. Everybody gets 4. Right? We're all okay with that. All I did was just write that down in this way. Or if you are stuck in the world of division operation, right? You just can't let go of division. Another way of looking at this would be to say that b divided by a equals c and integer, right? Which is the division operation. Division is for the reals, not the ints. But if you take an int, divide it by an int, and you get an int, that's a subset of the reals, right? You could say that, okay, fine. C is my number, that would work. Right? If you want to pull out a calculator, 3 divides 12. Why? Because if I take 12 divided by 3, I would get a 4, so all the 3 people get 4. Right? If you want to do it that way, you can do it that way. I personally don't recommend that. I personally say stay in the operations of the theory that you're working in. But this is fine. This is what the book defines, and other people like to do it as well. But we realize the weakness. There is no division operation in number theory. You're moving the problem to reals, realizing that you have all ints, and then saying, I have actually found what I wanted to get by using reals. All right. Some terms that go along with this. If A does divide B, you can actually have the following. The left is called a factor. The right-hand side is called a multiple. Or you could say that it is a divisor. Kind of like implication. If I say the word sufficient, which side of the implies are you on? The left. If I say necessary, you are on the right. Now, like in the same way, if I say I have two numbers, and I say, what is a factor? For this logical operator, with this bar, this logical bar operator, which side are you on? The left. If I say it's a multiple, which side am I talking about? The right. If I say divisor, the thing I'm talking about is on the left. And it's also, you have to keep in mind that this actually, again, what does this mean? This means that A times C is equal to B for C and integer. It's important to be able to understand that if I have the divide symbol, it actually is arithmetic algebra. Well, what's nice about arithmetic algebra? Well, all the things that I know of algebra come along. Because there's not a lot that I understand about this symbol, right? All I know is yes, no. And I have to have special cases. But on the other hand, what do I know about algebra? I can add things to both sides. I can subtract things to both sides. I can replace things with their equal. Algebra has all these laws that I already understand. So I can use algebra to answer questions about divisibility. For example, let's say we had a couple of things. Say the first, again, we're dealing with all ints. These are all integers, and A is not 0. This is true, that if A divides B and A divides C, therefore A divides B plus C. If it's true that A people can divide B objects and those same A people can divide C objects, if I took the two piles together and mashed them, the A people can divide that new pile. Could you prove this? Well, I don't know anything about divisibility, right? All I know about divisibility is what? What it means in terms of algebra. What does A divides B mean? That B is A times A int. Let's call it, say, N1. What does it mean for A to divide C? C is equal to A times A int. But they're not going to be the same, right? Because they're different numbers, usually. Here's a question. What's my goal? What's the right-hand side? A must divide B plus C. What does that mean? A times an int must equal B plus C. Well, here's my question. Well, if this above is true, what is B plus C? What do I have for algebra? What am I allowed to do in algebra? Can I replace things with their equal? What's B? It's equal to A times N1. What's C? A times N2. Common factor? A. So I can use algebra again, which is the actual distribution law, right? But what's an int plus an int? An int. So is B plus C A times an int? So is A factor of B plus C? Yeah. So that just simply means A divides B plus C. So we're done. So if you want to show some sort of new division thing, we have to go back to what I know, algebra, so that I can show it. But once I've shown it, from here on out, I can always use that. Here comes the part that a lot of students struggle in number theory, right? We leave algebra rather quickly. And we say, now we are going to use the word divides. And we're going to simply say, hey, look, A divides B and A divides C, therefore A divides B plus C. And I would never use algebra at all. I always have to think in terms of sharing. If A can share B objects evenly and A can share C objects, it can share their sum. Or any combination, and we'll get to some other features of that. The hard part is everybody always wants to keep going back to algebra, but to actually advance in actual number theory, you have to start shifting your thought process to only talk about things about like divides and what's this divides law and what's this divides law and what's this divides law. Is the divides operator commutative? No. Is it associative? Right? You have all these sorts of things. What does it do? What are features of it? And we have three of them right away. The second one is if A divides B, therefore A divides B times C. For any of these C's, which are obviously integers, is this anything actually new? Is this just the first? What does B times C actually mean? It means B plus B plus B plus B plus B plus, how many pluses have we done? C of them. But what does this top theorem say? That if you divide something, you must divide their sum. So what does this mean? If it divides B, it's obviously going to divide what? B plus B plus B plus B plus B. So it's really just the first one done C times. What about the third? If A divides B and B divides C, therefore A divides C. Why do you think that's true? What does B divides C mean? In terms of, if you can't do that, we would have to say 1 and 2 don't apply here, so I'm going to have to go back to algebra. What does it mean for B to divide C? B times an int is C. What does it mean for A to divide B? A times an int is B. All right, so wait. C is B times an int, but by the way, B is A times an int. So what's C? A times an int times an int. Is A a factor? Yes. And so you would just have to write that rather than what I said, and you would have your proof. But we were going back to algebra to do that. If I put all of those together, we would get a corollary, which is that if A divides B and A divides C, therefore A divides MB plus NC for any mn integers. This gets used a lot. Here's a question. What's the word lemma used for? It's a theorem that is mainly used to prove an actual important theorem. What's a corollary? It's a theorem, but it's a natural result of a more important theorem. That one, those three properties that I wrote, if we kind of jam them together, they're this. It says if A divides two numbers, it will divide any linear combination of them. That means it would divide their subtraction. It would divide 5 of one minus 4 of the other. It would divide 10 of one plus 1,000,000 of the other. It would still divide them all. All right, so those are properties that we can work with, and we use division, and we talk about mixing them up. If you divide things, we can divide any linear combination. Now let's get to a question. How do you share? All right, I literally mean this. It's like when a lot of times in mathematics we try to reduce things to what we see happening. And so Peano's axioms were the idea of addition, right, multiplication is actually addition, right? It's multiple additions. But is addition the fundamental property, or is there something that's even more fundamental below it? Peano's axioms, basically, you sit back and watch a kid. How do you teach them 2 plus 3? Well, what do? 2 plus 3, they put them together, and then what do? They count. So addition is actually counting. So counting is the fundamental thing that we must accept. So counting is the guy at the bottom that we have to build from. Well, okay, how do kids share then? And let's build up a mathematical model around it. If I had a pile of Skittles and kids sitting around, and we have to share these. You need to share the Skittles. What do? 1 for you, 1 for you, 1 for you, 1 for me. 1 for you, 1 for you, 1 for you, 1 for me. They just go and give everybody 1. But giving everybody 1 is what? It's subtraction. But you would look at it, oh, first they all had 1. Oh, my pile is bigger than the amount of people. I give them all now 1, which means they had 2. But my pile is bigger than the amount of people. I give them all another 1. Now everybody has 3. But my pile is still bigger than the amount of people. When do they stop sharing? When the pile is smaller than the amount of people, right? What does that become? Well, this is, I'll call it the sharing algorithm. If A is your pile, and D is the kids, what happens? Everybody gets a Q amount until there's left over, where the remainder is always greater than or equal to 0, but always less than D. So I would look at this and say, what am I sharing? A, which is the amount. Of course, that's not the actual word. This is called the dividend. D are the kids. It's not the word. This is the divisor, right? The people going up and doing the dividing. And then what happens? Everybody gets an nth Q. This is how much everybody gets. And that's the quotient. And then how much is left of the pile that I can't share, and that's the remainder. Everybody gets 1. Well, now everybody has 2. Well, now everybody has 3. Well, now we keep incrementing the quotient until we figure out that the remainder is the right number. It needs to be a positive number, right? That's smaller than the amount of people, or else I should have given people money or given people Skittles. Make sense? Mathematically, that says that, and this isn't called the sharing algorithm. It's called the division algorithm. We do not have a division operation. We do have a sharing, a dividing, a division algorithm, which is really what? How much does everybody get? How much is left over? And the algorithm is you just take 1 away from the pile and keep giving to people. It's a nice little loop. It tells us that there exists a unique QR integers such that this is true. Yeah, existential exclamation point means unique. The Q and R are unique. There are no other numbers that would make this work. As long as R is small enough, right? We go until we figure out how much everybody gets. All right, let's use this a couple of times. Let's say that the amount that we're talking about is 17 Skittles, and the amount of kids that show up are 4. So 17 is equal to, each of the 4 kids are going to get how much? 4. And once I've done that, what would be left in my pile? 1. If my amount is equal to 15 and the kids are equal to 3, everybody's going to get what? The 3 kids will get 5, and what will be left in the pile? 0. And actually, this introduces a neat feature. What's special of a remainder of 0? Remainder equals 0 says that the 3 can actually divide the 15 evenly. That's kind of an interesting feature. Oh, wait, if there's nothing left over, hey, that means fair share. The divides question is answered yes. So I've changed my question into simply yes or no, but a way of doing it. Find the remainder. If the remainder is 0, the answer is yes. What does it mean to say negative 15 and d is equal to, say, let's go to the 17. What about negative 17 and d is equal to 4? What does that mean? All right, think of the difference. I don't have 17 Skittles. Let's think of it this way. 4 people go out to eat. The combined bill is $17. I only have dollar bills. That's all that exists because we're in integer world. So if I only have dollar bills and I have a bill of $17, right, how much money should I collect from everybody?
Everyone is $4.
But if everybody paid 4, how much money would you have collected? Can that pay 17? So how much do I need to collect? $5 from everybody, right? So for negative 17, the only way this can work is that for the 4 people, I'm going to have to collect $5 from everybody. If I collect $5 from everybody, pay the bill, what's left over? A remainder. And what does the remainder always need to be? Positive, right? The remainder must be positive. I have to have a leftover. So you call that the tip, right? So in dollar bill world, right, you have this remainder of 3. You can't give it back to the people, right, because it doesn't divide evenly. The bill couldn't be shared evenly. I always have a remainder, so you either fight over it or just simply give it as a tip, right? But that's how negatives work. The way negatives work are you have to go through this and say, I have to collect enough to pay the bill, what's left over. So if the amount was equal to, say, $20 and everybody showed up with 3, how much are you going to have to collect from these 3 people to be able to pay a $20 bill? 7, which means that's minus 7. You've collected money from them, and what's left over? Which always leads to my favorite issue of trusting the speaker and he's a manipulator. 3 guys, they went on a hunting trip. And so they're going out to western Kansas, and they're going to go, oh, let's just share a room. We'll just crash here and go hunting in the morning. And so they come in. It's like, well, how much is this? It's $30. It's hunting season. It's like, so all right. So they each pay $10, and then they go to their room. And the manager comes up later and asks, he goes, wait, were they actually hunting? Yeah. It's like, oh, no. They don't actually need to. There's a $5 discount during hunting season. They didn't have to pay $30. They were supposed to pay $25. So he's like, okay. And so he collects 5 $1 bills, and then he's walking into their room, and he's like, oh, man, there's 3 guys. I've got $5 bills here. You know, they're going to fight. I mean, because it doesn't share evenly. I know what I'll do. I'm extra helpful. I'm going to pocket $2. So he puts $2 in his pocket, and then gives them each back $1. So how much did each of them actually pay? They paid 10 originally. They got $1 back. How much did they pay each? Actually, 9. Well, what's 9 times 3? 27. Well, there's $2 in the kid's pocket, 28, 29. Where's the other $1? No, he gave himself 2. He had $5. He has 2 in his pocket. He gave them back. They paid 9 each. That's 27. There's 2 in his pocket, 28, 29. Where's the other $1? I'll let you think about that till tomorrow. Or actually, no. Next class. All right. What we can do here for this division algorithm, Q times D plus R, since this and this are important, I can turn this into an operation that say A and D come in and it'll just simply immediately tell me what Q is. In other words, we could sit there and call this the div. Q is equal to A div D. Normally this is coded as div AD. And then the R is equal to A mod D, normally written as mod AD. All right, obviously A is amount, D is the divisor, right? A is the dividend, D is the divisor. So if I'm doing that particular feature, are these commutative? Again, A is like money and kids. Can you just flip those around? No, you can't. So it also means when you code, when you have programming languages, obviously order matters. So you better know what order they're doing. But then for above, we had our above example. What is negative 17 div 4? What was that?
Was it 5?
Minus 5, right? Everybody has to pay $5. Negative 17 mod 4. What's that? If everybody pays $5, there is $3 overpay, right? So the div and the mod immediately spit out. So now what do we have for operations? Our new number theory operations are what? I know how to add, I know how to multiply, I know how to ask the question of divides, and I know a div d, a mod d, both of which are based upon the sharing algorithm, the division algorithm of asking for the quotient or the remainder. Now, having this, especially this question here, having the division algorithm introduces a new question of sameness. The first one is obviously, I know that 3 being 1 plus 2, you know the idea of equals. We all understand what equality means, right? Same amount, right? So we all understand equality. Now what we're going to talk about is a new type of same for next class, and that is congruence. And congruence has 3 forms. First form, let's see, m divides a minus b. Second form, a mod m equals b mod m. Or the third form, a is b, but it's just some sort of multiple. And this is congruence, always mod m. And if that's true, we would say that a and b are the same. So one of those 3 things are they all mean the same thing. And so next class we're going to talk about this new type of sameness. These numbers are the same, but we're going to call it the word congruent. And we'll do that and have applications of it, and it's rather powerful. The attendance problem is number 7 for this section. Attendance 4.1, number 7. All right, that's it.